This is the Math 2 Honors review for Unit 0. Number 1, we have 3x to the power of negative 4. First thing I'm going to do is to write the reciprocal, which is 1 over 3x to the power of positive 4. I'm getting rid of the negative exponent. The way to do that is to move the expression to the other side of the fraction. Next, I'm raising both the 3 and the x to the power of 4. So I'm going to rewrite this as 1 over 3 to the power of 4 times x to the power of 4. And lastly, we can find 3 to the power of 4. 3 times 3 times 3 times 3 is 81. And so our final answer is 1 over 81 x to the power of 4. Number 2, we're asked to multiply two expressions. You multiply things that are alike. So the 2 ends up being multiplied with the 5, you get 10. The y to the third, you end up multiplying with the y to the 7. But we have an x to the 5th prior to that, and so I'm going to include the x to the 5th first, and then multiply the y to the 3rd and the y to the 7th by adding exponents. 3 plus 7 gives you 10, so it's y to the power of 10. And then lastly we have a z. So our final answer is 10 x to the power of 5 y to the power of 10 times z. Number 3, notice we have exponents outside of the parentheses. We have to deal with those first before we multiply everything else together. So everything inside of the first set of parentheses, I'm going to square. So we have 3 to the power of 2, x to the power of 2, y to the 3rd to the power of 2, z to the negative 2 to the power of 2. In the second set of parentheses, everything is raised to the 3rd power. So we have 7 to the power of 3, x to the power of 4 to the power of 3, y to the power of 0 to the power of 3, and z to the power of 4 to the power of 3. Three squared is 9. X squared, y to the 3rd to the power of 2. When you have a power, you multiply those exponents, and so you end up with y to the power of 6. Same idea with the z. Negative 2 times 2 is z to the negative 4. Times 7 to the 3rd power is 343. It's 7 times 7 times 7. X to the 12th. Y to the 0 is 1. And, well, I'm going to multiply first the 0 and the 3, but this is still y to the 0, because 0 times 3 is 0, and anything to the power of 0 is going to be 1. And then lastly, we have z to the power of 12. We're going to continue multiplying. I'm going to multiply 9 times 343, which is 3087. X squared times x to the 12th power. You add your exponents, you get x to the 14. Y to the 6, y to the 0. Again, you add your exponents. 6 plus 0 is still 6, so y to the power of 6. And z to the negative 4 times z to the 12th, you add your exponents. You have a negative number plus a positive number, you end up with z to the power of 8. And that's our answer. So number 4, 32 is 2 to the 5th power. And you can break down 32 as 2 times 16 and keep breaking down the 16 as 2 times 8 and so on. But you eventually end up with 32 as 2 times 2 times 2 5 times. And we have x to the 5th, which means x times itself 5 times. Y squared means y times itself, and z to the 7th. So we have the same exact expression, just factored out. When we're simplifying a square root, we're looking for pairs of things. So if we find any pair of things, we can take the square root of that. So for example, we have a pair of 2's here. 2 times 2 is 4. We can take the square root of 4, which is 2. Here's another pair. So I'm going to circle all the pairs of things that we can remove from underneath the square root. So we end up with 2 times x times y times z to the 3rd. And we're left with everything we didn't circle, the 2xz beneath the square root. Simplifying this now, 2 times 2 is 4, x squared, y, z to the 3rd, square root of 2xz. And in this problem, we're going to assume all variables are positive. So that's our answer. For number 5, we're looking for the cube root of 4,116. In order to get anywhere with this problem, we're going to have to break that number down into smaller factors. So over here on the left-hand side, I'm going to rewrite the number 4,116 and try to think of two numbers that multiply to that number. First thing that comes to mind is it's an even number. So if I divide it by 2, half of 4,116 is 2,058. Again, it's even, so I'm going to cut it in half again. 1,029. It's no longer even, so we have no more factors of 2, and so we can try some other things. Ends in a 9, we could see, well, maybe this is divisible by 3, maybe it's not. Like 29 is not divisible by 3, but let's try it out, and in fact it is. So if you divide by 3, you end up with 343. If you try dividing by 3 again, it doesn't work. 4 is not going to work. 5 is not going to work. 6 isn't going to work. When you try 7, it does. This is 7 times 49. And 49 is 7 times 7. So what we end up with is the cube root of 2 to the 2nd power times 3 times 7 to the 3rd power. In this problem, we're taking the cube root, so we're looking for sets of 3, and we have 3 7s, and that's the only thing we have a set of 3 of. And so we can pull out those 3 7s. We get 7 times the cube root of what's left. 2 squared is 4 times 3, which is ends up being 12. So 7 cube root of 12. Number 6, we want to simplify this expression. We're multiplying two radicals, or two square roots. Before we do that, I encourage you to break down the numbers 60 and 98 and see what we're working with here. So 60 is 6 times 10, and 6 is 3 times 2, 10 is 2 times 5. 98 is 2 times 49, and 49 is 7 times 7. So when you multiply 60 and 98 together, instead of multiplying them together, just string their factors right next to each other. So we end up with 60 has 2 2's, and 98 has 1 of the 2's. Back to 60 we have a 3, a 5, and then back to 98 we have 2 7's. So if I were to multiply 2 times 2 times 2 times 3 times 5 times 7 and get that answer, it would be an equivalent answer to multiplying 60 and 98 together. But now I can see the prime factors of whatever that product is without even knowing what the product is, and that's going to help me simplify the square root when I need to. X to the fifth times x to the third, you add your exponents, you're going to get x to the power of 8. Y squared times y to the third, add your exponents, you get y to the fifth. And because we're taking the square root, we're looking for pairs. So we have a pair of 2's and a pair of 7's. We also have an even number of x's. We have 8 of them. And so we can think of that as x to the fourth times x to the fourth. So we have a pair of x to the fourths. Y to the fifth, we can break that into 5 y's, or we can see that as y squared times y squared times y, which is still y to the fifth. And we have a pair of y squareds. So as we simplify this, we're going to end up with 2 times 7 times x to the fourth times y squared on the outside of the square root sign. And what's left is 2 times 3 times 5 times y. And continue simplifying, we end up with 14 x to the fourth y squared times the square root of 2 times 3 times 5 is 30 y. On number 7, again we want to simplify and combine like terms. We're working with fourth roots here. So your choice, we can simplify the numbers first like we did in number 6, or we can combine everything first and then simplify. If we combine everything first, here's how I would do that. 3x times 5, notice that little 4 is not x to the fourth power, it's 3x alone, and then that's the fourth root. And same idea here, it's not 5 to the fourth power, but it's 5 times the fourth root. And so as we multiply things together, we end up with 3x times 5, which is 15x, times the fourth root. Now I would not multiply 135 and 375 together because you need to factor them anyway, so just write them right next to each other. 135 times 375. We have an x to the 8th, and we have a y to the power of 10 because we're adding the 7 and the 3. So we're working with a fourth root, and when we simplify a fourth root, we're now looking for sets of 4. So we want to factor out these numbers and look for as many sets of 4 as we can. So 135 is 5 times 27, and so I'll write it as such. So 5 times 27, but remember 27 is 3 times 3 times 3. Okay, so you break down the 135. I'll do it over here. 135 is 5 times 27. 27 is 3 times 3 times 3. And 375, because it ends in 75, you know it's a multiple of 25. In fact, it's going to be 15 times 25. And 15 is 3 times 5. And 25 is 5 times 5. We have 8 x's. And 10 y's. And we're taking the fourth root of all of that. And we still have the 15x out in front. So simplify this further. We're looking for sets of 4. So we have 4 x's here, 4 x's here. We get 4 y's. Another set of 4 here. 2 y's are going to be left over. We have 4 5's. And we have 4 3's. So cleaning this up, we end up with 15x times 5 times 3 times x times y times the fourth root of what's left, which is y times y. Keep going. 15 times 5 times 3 is 15 squared, or 225. We have the x next to the 15 times the other two x's, so we end up with x cubed. Y squared, fourth root of y squared. That is our answer. On number 8, we're adding two radicals. The rule is we can only add radicals if they have the same number underneath that radical sign. In this case, the square root of 80 and plus the square root of 45, we can't directly add. But if we simplify them first, we may find that things change and allow us to add them. So let's try to simplify them. 80 is 8 times 10. 8 is 2 times 2 times 2. And 10 is 2 times 5. With 45, we end up with 5 times 9. And 9 is 3 times 3. So we can rewrite these as the square root, well, we're pulling out pairs. So 2 times 2 times the square root of 5 plus, we got a pair of 3's, 3 times the square root of 5. Or 2 times 2 is 4, so 4 root 5 plus 3 root 5. Now we can see they both have a root 5. Because of that, we can add the coefficients, 4 and 3. And our final answer is 7 square root 5. On number 9, 108 is 4 times 27. 4 is 2 times 2. 27, 3 times 3 times 3. Keep working on those numbers, break them down to their prime factorizations. 32 is 4 times 8. 4 is 2 times 2. 8 is 2 times 2 times 2. Here we're looking for sets of 3 because it's a cube root. So we have 3 sets of 3 here, and we can grab 3 sets of 2 on the right hand side. So let's see what we end up with. On the first cube root, we have a 4 out in front already. And then that 108 broken down, we have 3 3's, which convert to 3. When you take the cube root of 3 cubed, you end up with 3. And we're left with the cube root of 2 times 2. Plus, in the second expression, we have a 3 already out to begin with in front. We have a set of 3 2's, and we're left with the cube root of 2 times 2 again. So that is equivalent to 12 cube root 4 plus 6 cube root 4. Both expressions have a cube root 4. We can combine them, and our final answer, we add the 12 and the 6 to get 18 times the cube root of 4. On number 10, we have a fractional expression raised to the third power. We can raise everything to the third power, work with that cube on the outside of the fraction first, or we can try to reduce that fraction prior to raising everything to the third power. I'm going to try to reduce that fraction first because I notice there's a 7 over 21. I can make my numbers smaller there, and I'm going to work with that. So I still have everything in parentheses. I still have that cube on the outside of the parentheses, but I'm going to reduce the 7 over 21. Divide the top and bottom of the fraction by 7, you get 1 over 3. That x to the negative third power, I'm going to move to the denominator, make it x to the positive third power, and I'll leave the y squared in the numerator. Now I got smaller numbers to work with, that a 3 instead of a 21, and it'll be easier to cube. So 1 cubed is 1. Y squared to the third power is y to the 6. I multiply the 2 and the 3. 3 to the third power, 3 times 3 times 3 is 27. And then x cubed to the third power, you multiply the 3's in that case because they're both exponents, an exponent of an exponent, and you get x to the power of 9. And that's all we can do, and that's our answer. Number 11. On this one, we cannot reduce the fraction first because the whole fraction's not in this set of parentheses like in number 10. We're going to have to work with the numerator and denominator separately at first, and then we can simplify further. So I'm going to square everything in the numerator. So 3 squared is 9, 3 times 3. X to the negative 2 squared, you're multiplying the numbers, the exponents. And so you get x to the negative 4. Y to the 4th squared is y to the 8th. Over. Now, here I'm going to raise everything to the negative third power. So I'm going to write 12 to the negative third. X to the negative 15. And y to the positive 15. And anything with a negative exponent, I'm going to move to the other side of the fraction. So the 9 has a positive exponent of 1. We don't see the 1, but it does, so we're going to leave the 9 there. The x to the negative 4, I'm going to move to the bottom, make it x to the positive 4. Y to the 8th, I'll leave up here. 12 to the negative 3, move it to the top. 12 to the positive 3. X to the negative 15, move up. And y to the 15, keep in the denominator. So 9 times 12 to the third power. So first figure out what 12 to the third power is. And that's 1728. And then multiply that with 9. And we get a big number. We get 15,552. Then we're dividing. We have an x to the 15 divided by x to the fourth. When you divide, you subtract your exponents. So 15 minus 4 is 11. We started with more x's in the numerator, so we'll end up with 11 x's in the numerator. And then again, subtract your exponents with y. 15 minus 8 is 7. But we started with more y's in the denominator, so we're going to end up with our y's in the denominator. And that's our answer. Number 12, we're multiplying two exponential expressions. When we multiply, we add the exponents. So this is equal to 3 to the power of 2/3 plus 3/2. When we add fractions, we need a common denominator, which in this case is going to be 6. So I'm going to change our fractions. The first fraction I'll multiply by 2 over 2, which is going to be make it 4 over 6. I multiply the 2 by 2 and the 3 by 2. The second fraction, I'm going to multiply the top and bottom by 3 and get 9 over 6. Now we have a common denominator. We can add those fractions, end up with 3 to the power of, remember when you add, you only add the numerators, so 9 plus 4 is 13 over 6. Number 13, we are in a fraction form. You can think of that as division. We're trying to simplify it or condense it into one expression as much as we can. Let's change it out of radical expression into exponential. So the first one is the square root, there's an invisible 2 there, of 4 to the third. That's the same thing as 4 to the 3/2 power. Over, in the denominator we have the fifth root of 4 to the fourth, so that's 4 to the 4 over 5. Here we now see the base is 4 and we have two fractional exponents. When we divide, we subtract the fractional exponents. Think about, well, which number is bigger, 3 over 2 or 4 over 5? 3 over 2 is 1.5 as a decimal. 4 over 5 is 0.8 as a decimal. So the number in the numerator is larger. And so I'm going to subtract 3 over 2 minus 4 over 5. We need a common denominator just like we did in number 12, which will be 10. So multiply the 3 over 2, the 3 and the 2 by 5 and get 15 over 10. And multiply the 4 and the 5 by 2 and get 8 over 10. We can subtract the 15 and 8 to get 7 out of 10. And so that may be, that's an acceptable answer, and that if it's a multiple choice question, that may be the answer you're looking for. It may look a little different too, because 4 is 2 squared. So we can do a little more work with this. We can write 2 squared, that's my 4, to the power of 7 over 10. Well, if I multiply 7 over 10 times 2, I end up with 2 to the power of 14 over 10, which reduces to 2 to the power of 7 over 5. So that is as much as we can do. For the test, know both of them, but know that they're both equivalent, that you may have to choose either as an answer. Number 14, I'm going to get out of radical form. So we have an x to the 4/5, and then the cube root is the 1/3 power. And so we have a power of a power, and you multiply fractions here. We do not need a common denominator. 4/5 times 1/3, you multiply the 4 and the 1 to get 4, and the 5 and the 3 to get 15, and there's your answer. Number 15, we're simplifying here. We are not allowed to end with a radical in the denominator, and so because it's a square root, I'm going to multiply by a square root of 7 to create a pair of 7s in the denominator. And so this gives us 3 square root of 35 over the square root of 49, and we know the square root of 49 is 7. So we are able to rationalize the denominator, make the denominator a rational number. Square root of 7 is not rational, but 7 is. On 16, we want to rationalize the denominator there as well, and we need to be a bit creative here. It's a cube root, so we have 1 3. We're going to need a set of 3 3s, so I'm going to multiply that by the cube root of 3 times 3, which is the same thing as the cube root of 9. And so we end up with 10 times the cube root of 9 over the cube root of 3 times 3 times 3, which is 27. Cube root of 27 ends up being 3. We have a cube root of a fraction. You are able to split that cube root up between the numerator and denominator, so we can write cube root of 4 over cube root of 9. And it's okay to have a root in the numerator, so we're not focused on that. We're focused on the denominator, getting rid of that cube root of 9. 9 is 3 times 3, so it'd be nice to have another 3, so I'm going to multiply by the cube root of 3. And that gives us a set of 3 3s. So we end up with the cube root of 12 divided by 3. If you were to multiply the 9 and the 3, you'd get 27 like the previous problem in number 16. And we get the cube root of 27, which is 3. Number 18. Initially, it may not be obvious that there's anything to do here. Check the base of the 27. Ask yourself, is 27 a power of some number? And in fact it is. 27 is 3 to the 3rd power. And we already have the exponent 4/3 on top of that. So multiply your exponents. So this is 3 to the 12 over 3. And reduce. 12 over 3 is 4, so this is 3 to the 4th power. And we can keep going. 3 to the 4th power is 3 times 3 times 3 times 3, so this is 81. Number 19. Notice we have a negative number, 32 here. and a negative exponent, that 1/5. It's okay to have a negative number. It's not okay to have a negative exponent. So the negative number stays negative. Nothing's going to change that. But the negative exponent we can make positive. I'm going to rewrite this as 1 over negative 32 to the power of 1/5. Now, did I have to get rid of that negative exponent first thing? No. Eventually you had to get rid of that negative exponent. I just chose to get rid of it in the start. Sometimes we'll get rid of it at the end. It didn't matter. It doesn't matter in this case. Looks like we're done. But again, like in number 18, check the base. 32, negative 32. Is negative 32 a power of some number? And it is. It's the power of negative 2. It's the 5th power of negative 2. So negative 2 to the 5th power, that's my negative 32. And all of that is raised to the 1/5 power. Now I can multiply my exponents, the 1/5 and the 5. And I end up with 5 over 5, which is 1. So this is really 1 over negative 2, or negative 1/2. Number 20. We have a big number, 2025, which we can guess it's divisible by 25 because it ends in 25. And it is. It's 25 times 81. 25 is 5 times 5, or 5 squared. 81 is 3 times 3 times 3 times 3, or 3 to the 4th power. So I'm going to rewrite this as 5 squared times 3 to the 4th power, x to the 9th, y to the 5th, z to the 3rd, all to the power of 1/3. Now I'm going to raise everything to the 1/3 power. We do that by multiplying those exponents by 1/3. So we end up with 5 to the 2/3 power, 3 to the 4/3 power, x to the 9/3 power, y to the 5/3 power, z to the 3/3 power. Some of these reduce, some don't. It may have been better to do this a little different way, and I'll mention that at the end, but notice what does reduce. The 9/3 power becomes the 3rd power, and the 3/3 power becomes 1. So here we have 5 to the 2/3 power, 3 to the 4/3 power, x cubed, y to the 5/3 power, z. All the parts that have a fractional exponent with 3 in the denominator, remember that's really a cube root. So the 5 squared, the 3 to the 4th, and the y to the 5th are all inside of a cube root, where the x cubed and the z are not. So this is equivalent to x cubed z times the cube root of 5 squared, 3 to the 4th, y to the 5th. We can simplify that further. Remember, if it's a cube root, we're looking for sets of 3, and we have This is 3 to the third power times 3, and this is y to the third power times y squared. So we have a set of 3 3's and we have a set of 3 y's that we can pull out of this. And so then final answer, we end up with 3, pulled the 3 3's out. X cubed was already out. Y to the third, so it just becomes y. And then z, that's on the outside, times the cube root of what's left. We have a 5 squared times a 3 times a y squared. Just be careful keeping track of all the little pieces. And then we can multiply 5 squared times 3. So final answer, 3x cubed y times z times the cube root of 25 times 3 is 75, y squared. Now I mentioned earlier that there might be a better way to approach this, and I'm going to point that out right now. So up front here, instead of kind of distributing that 1/3 power, think of it automatically as a cube root of the whole thing. And we'd end up here. And then take the cube root of each piece. We're looking for sets of 3. We only have 2 5's, not going to work there. We have 4 3's, so we can say, well, we got 3 3's and 1 3. That makes 4. We have 9 x's, and we're looking for sets of 3, so I could break that. Well, that's x cubed times x cubed times x cubed. We have 5 y's, so we can say, well, we got 1 set of 3, and then 2 left over. And then we have 3 z's. And so I'm going to highlight the sets of 3. Well, actually, that's my set of 3 there, set of 3 there, set of 3 there. And so when we pull everything out, that's a set of 3. We end up with 3 x cubed y z outside, and we're left with 25 times 3, which is 75 y squared. So we get the same answer, less work. There's still a lot to think about in this problem, so just be very careful. I'd probably go with that second approach, a little less work there. Practice that one. 21. So everything's raised to the 1/2 power. Remember, 1/2 power means the square root, so that may be helpful as well. Either way, we can think of it as a square root or as a 1/2 power. I'm going to think of it as a square root. So we're taking, this is equivalent to the square root of 25 x to the 8 over 3y to the 5th. And then I'm going to split them up. So we have the square root of 25 x to the 8 over the square root of 3 y to the 5th. And remember, with a fraction, you can't have a root in the denominator. So we need to rationalize that. Notice that the numerator is a perfect square. 25 is 5 times 5. X to the 8 is x to the 4th times x to the 4th. So we can automatically simplify that. So we end up with 5 x to the 4th in the numerator. The denominator, we could simplify a little bit. We're looking for pairs. We have y to the 5th already. Split that up to y to the 4th times y. And y to the fourth, we can take the square root of y to the fourth, that's y squared. And we're left with the 3y underneath. It's your choice if you want to simplify now or later. Usually if you simplify first, you do a little less work. Gotta get rid of that square root though. I have a square root of 3. I'm going to multiply by another square root of 3. That gives me 2 3's. I also have the square root of y, so I'm going to multiply by another square root of y. Got it. Whatever you do to the numerator, you got to do to the denominator to keep the expression equal. So multiply, and you end up with 5x to the fourth times the square root of 3y all over y squared times 3 times y. Simplify that denominator a little bit. 5x to the fourth square root of 3y all over 3y to the third power. That's as much as we can do. Number 22. '81 is 3 to the fourth power. So if you recognize you're working with numbers that are powers of other numbers, change them. Usually simplifies the process. Now everything's raised to the 3/4 power, so I'm going to multiply that 3/4 with those two exponents, the 4 and the 2. And we end up with 3 to the 12/4 power. And x to the power of 6/4. And then reduce. So 3 to the third, x to the 3/2. Number 23. Write an expression in the form a to the power of m to the power of n that is equivalent to a to the power of -20. Notice in this expression, this is the same thing as a to the power of m times n, and that's where the -20 is. So we're thinking of two numbers that multiply to -20, and we have many different options. So just pick two that work. So -4 and 5. And we can write that as a to the -4 to the power of 5. You can switch those, make it a to the 5th to the power of -4, or you can come up with another combination that works. 24. Provide a counterexample showing that the following statement is false. A counterexample is an example that shows a statement false. Okay, so the statement is the product of any two irrational numbers is always rational. Now that may be true in some cases, but we're saying that it's not true always. So we're trying to come up with two irrational numbers that we multiply together and come up with another irrational number. So if I said like square root of 7, that's an irrational number, times the square root of 7, those are two irrational numbers. If I multiply them together, I end up with 7. That's rational. So that's not a counterexample. That's not what we're looking for. If I do the square root of 7 times the square root of 2, those are both irrational numbers. If I multiply them together, I get the square root of 14. I can't do anything more. I can't get rid of that square root sign, so it stays irrational. And so that's my counterexample that shows that statement false. 25. Find a number that you can multiply with the 4th root of 9 to get a rational answer. Well, if you break up that 9, this is really the 4th root of 3 times 3. And if I want a rational answer, I'm going to have to make a set of 4. So if I multiply that by the 4th root of another 2 3's, you end up with the fourth root of 3 times 3 times 3 times 3, which is 3. So what would you multiply the fourth root of 9 by to get a rational answer? I would multiply it by another fourth root of 9, right? Because this is the fourth root of 9. Sorry. That's the fourth root of 9, and this is another fourth root of 9. And when we multiply them together, we got 3. So answer, fourth root of 9. 26. Is the cube root of 100 a rational or an irrational number? Explain. So in order to answer that, we try to simplify it as much as we can. If we're able to get rid of the cube root sign in our answer, then we say it's rational. If we're not able to get rid of that cube root sign, we'll say irrational. So the cube root of 100, well, we know 100 is 10 times 10, or 2 times 2 times 5 times 5. We're looking for sets of 3. We don't have 3 of anything, so that just remains the cube root of 100. We weren't able to get rid of that cube root sign, and so we say it is irrational. And then the square root of 81, that's 9. And so it's rational. There's no square root sign. Okay. Number 28. We got the cube root of x times x to the 1/4 over the square root of x. I'm wanting to simplify that. I'm going to change everything to fractional exponents. So cube root of x is x to the 1/3 power. We have an x to the 1/4 power here. And we have an x to the 1/2 power. And so I'm going to multiply these two fractions together. And so we end up with x to the 1/3 plus 1/4 in the numerator over x to the 1/2 in the denominator. Need a common denominator to add fractions, so x to the 4/12 plus 3/12. I multiplied the first fraction top and bottom by 4, second fraction by 3, over x to the, I'm going to make this something over 12 as well, because it's going to help with the next step. So that's 6/12, multiply top and bottom by 6. So we end up with x to the 7/12 over x to the 6/12. And then you subtract your exponents, and you end up with x to the 1/12. Last one, number 29. And it says find the square root of x to the 4th if x is negative. Now, up to this point, we've assumed that when we are taking the square root of variables, that the variable is positive. But let's now assume it's negative. Let's try this out with, pick a negative number. Let's let x be -2. So then our problem would be the square root of -2 to the 4th power. And so when we work that out, well, -2 to the 4th power is +16. And then the square root of 16 is 4, which we can think of as 2 squared. So notice we had a negative 2 to the fourth. We ended up with a positive 2 to the second to end with. But which is positive 4. We can also think of that as negative 2 squared, right? Because 2 squared is positive 4, negative 2 squared is positive 4 as well. And so the square root of x to the fourth would still work as x squared.